Hello, everyone. Thanks for joining the Tech Talk in Edinburgh PL team. And we are honored to invite George, which is a PhD student from University of Birmingham. And he also joined the Edinburgh PL team a month ago and to give us a Tech Talk. Yeah, maybe George, you can also give a brief introduction of yourself and the topic today.
Okay. Yeah, hello, I'm George. So I'm at University of Birmingham. I'm being supervised by Dan, so I just can't get away from him wherever I go. I'm always under Dan's supervision somewhere. But today I'm going to be talking about diagrammatic semantics for symmetric traced monoidal categories. And that might sound a bit scary, but I'll explain everything as we go along. So first of all, what is the point? Why do we care about these categories? Like, category theory is just abstract nonsense, right? Surely there's no actual reason we need to use it. Well, it turns out that category theory is actually very good for compositional processes, which I guess is the whole point, really. If you have, say, a process, this box F, maybe with some inputs and some outputs, we can stick it together with another one. We can do F followed by G, or perhaps we could just put them on top of each other, do an F on top of G, or F tensor G. And this sort of compositional framework crops up in all sorts of places. I mean, the most probably famous one is the quantum computation work with all the spiders and various wires and things. But also it crops up in things like linguistics or electrical circuits with transformers and things. And the one thing that we're interested in is digital circuits where we have logic gates, like and or, and all those things. And the good thing about using this categorical framework is that we can model sort of semantics for these systems of processes using our language. We can represent our system with equations that we can then use to reduce terms down to something more simple. So say we take this circuit here, we have a true and a false going into an AND gate. We could write that as this. We could do true tensor false, true on top of false, followed by an AND. And hopefully everyone knows that that should reduce to a false. I think it does. I should certainly hope it does. And that is an example of how we can sort of identify this red X, this true tensor false, followed by AND, and say, oh, actually, we know that's just a false. So that sounds pretty great, right? But then, so let's have a look at a bigger example, this one here. So you might think, oh, well, what about this? We say, oh, it's true tensor false, followed by an AND, all on top of this one false, and then we stick it all into this OR at the end. And indeed, yes, we've got this red X here that we can reduce here to a false. And then again, false and false into an OR is still false. That's great. But as you might be able to see, there's not just this one way of representing this diagram. There's all sorts of things, because this is a two-dimensional diagram that we're doing, and we're trying to represent it as this one-dimensional string. So what about something like this? We could do it in these slices, this true, false, false, and then this AND followed by this empty wire, and then all put into this OR at the end. And there's no red X's in this. There's nothing you can see that we can reduce. And while there are axioms we can apply to sort of rearrange things to get to something with red X's, that's quite hard to do. And like, if you want to feed this to a computer, and you want a computer to go, oh, here's the red X, reduce down to nothing, it would have to go, oh, well, actually, I've got to do all this housekeeping first, and that would take ages, and we don't want that. So that's one problem about using just this sort of term string representation. And also just another one, on maybe a less serious note, so say if you have an even bigger circuit, like this flip-flop, and that is this. And what is this? Like, I don't know what this means. This is just the letters and numbers. It's completely undecipherable. And this is another reason why we might want to actually use a diagrammatic representation like we have with our circuit diagrams. And we just want to have this as a formal diagrammatic language for our categorical framework. Yeah. So before I carry on, I don't have any questions just from that. Guess not. So I'll give everyone sort of a crash course on these monoidal categories just to hopefully get everyone up to speed and these graphical languages. So the basic building blocks of our categories is these generators, these individual processes that have some inputs and some outputs. And as we know, we can stick them together. If the outputs of the generator is the same as the inputs of another, we can just stick them together, have F composed of G. And an important thing that categories have is this notion of identity morphism. This just wire which does nothing, it returns the same thing. You give it one thing, out comes another. And with identities, as you can just extend a wire on a process any way you want. You can sort of put in these identities or take them out, and that's fine. That's completely allowed. And have these diagrams here. Now, we've had our sequential composition, but what about putting on top of each other? And for that, we need the tensor product. And that means if we have just any two processes, we can just whack them on top of each other like this, and we get F tensor G. It's just them on top of each other. And again, like how we had the identity for the normal category, we also have a sort of identity here, and that is the empty space, this empty thing where I is just the unit, as it were. And we can, again, smash this empty space anywhere we want, and it won't affect our diagrams. That's good. So everything we've got, sorry about that. Everything we've got, we can have things going from left to right, on top to bottom, and that's great. But we need a little bit more than that to do any sort of interesting diagram. But first of all, have a look and see if we've already solved the problem we had before. So before we had this way that we could represent things on top of or left to right in numerous different ways. So we could have this way, where we sort of look at this bit composed with this bit, or we have this version where we have the sort of sequential one first on top of this one at the bottom. But actually, as you can see, the diagrams are the same. So that's good. We've solved our problem. So one of our problems is that with the diagrams, we don't have to do any of this housekeeping or anything. We just can look at the diagram and go, oh yes, they are obviously the same. So we're done. And yeah, bureaucracy is no more. So as I was saying, we want to add some more sort of structure to our categories. We don't want to always have wires going maybe like on top of each other like that. We want to be able to cross over our wires to, well, do all sorts of things. So for that, we've got this new generator, which is all it is. It just swaps over the wires. And with this symmetry, we get a few axioms that we can use to manipulate our diagrams further. We have this naturality axiom, which if we have something on a symmetry, we can always push it through and have it on the other side. As you can see, the diagrams, all the connectivity is still the same. We have this hexagon axiom, which is just sort of a housekeeping for multiple symmetries. Just we can combine them into one big symmetry. And quite importantly, that this symmetry is a self-inverse. If we do a symmetry followed by another one, we're just going to get two identities on top of each other because it's sort of all done. That's good. And then with our diagrams, normally we're not actually really concerned with sort of these objects or the inputs. We're just concerned with the number of wires coming in and out. So for that, we just have this thing called a prop, which is all the objects, these A's and B's and C's are just numbers. So from now on, you can think of just a box as inputs is a number of wires coming in and a number of wires coming out. And finally, what we want to do is to wrap all this stuff up together to make lots and lots of big diagrams. So we have what's known as a free category, and we have a signature containing some generators, and then we can stick things together to create terms. And all it is just by applying composition, tensor, putting some identities and symmetries in, and we can make our big diagrams. So does anyone have any questions about sort of these three categories up to now?
Yeah, I guess what's the, are we still thinking of digital circuits at this point? And if so, what does the fan in sort of mean?
Yeah, you can think of this, well currently we haven't got feedback, which is what I'm about to do in a sec, But you can still think of these as, well, this is just sort of like a fork, like a forking thing, and maybe this is to join some wires. But these just processors and things. But yeah, but next up is feedback, which is obviously a very important thing, digital circuits. So far, all the wires have gone from left to right across the screen. We've had things coming in, and then doing some stuff, and going out. But sometimes we need more than that. So like in digital circuits, we have feedback. We have something coming out of the right and go whoosh, all the way around, back to the start, and putting something else. But so can we bend our wires in somehow? So the classic sort of normal way of doing this is to use what's known as a compact closed category, where we have these morphisms just to bend the wires, and we can stick these onto the ends. And this works for a lot of things, like in the quantum computation stuff, they all use this compact closed stuff. But this is because compact closed categories have a flexible sort of causality, that there's no notion of really inputs and outputs sort of happening in order. You can sort of go in whichever way you want. But then in our digital circuits sort of way, well, you can't feed something into the outputs of an AND gate. Like, what is that? That's not a thing. You blow it up. So we don't want to have a diagram that looks like this. This is not allowed. So yeah, this is bad. But fortunately, there's sort of an intermediate notion, and that's known as the trace, and that is the trace of the symmetric traced monoidal category. So unlike having to bend, like these bendy curved boxes, we actually do a trace as one single atomic action. We take the first wires, and we just take it all the way around, connect it to the inputs. This is the trace. And this means that all of the outputs of boxes can still only connect to the inputs of boxes. We can't have this suddenly go into another output, because you always have to go all the way around. That's what we want. So again, there are some sort of useful housekeeping axioms here. If we have a big trace, we can sort of suck it in to make a small trace. If we have a symmetry and then a trace going around, well, then we just sort of yank it out and make just the identity. And you see, yeah, this also makes sense. They follow the wire around, and it is just the identity. If we have a trace sort of going over multiple things, we can sort of put it up a bit, just to make a smaller one again. And finally, we're allowed to swap over the orders of traces as long as we swap them back over at the end. And again, just like with our sort of normal symmetric monoidal categories, we can just do a free trace category by combining all the operations of composition, tensor, symmetry, and now our trace to have something like this. And for now on, I just have this sort of prop in the back of our mind, which is called term sigma, which just contains this signature with these fork and join wires, and they'll be coming into play later. So as you can see, all these diagrams are great. We can just have all these things over our screen, and they get rid of us having to rearrange stuff, having to apply these axioms, this yanking, tightening, whatever. And that makes things a lot easier. But so does this solve all our problems? And you might be thinking, yes, please, I want to go home. But no, it does not solve all our problems. And why is this? Because normally we're not just dealing in a vanilla trace category. Normally we've got some extra structure on in the form of some more axioms. So one example which I think we'll look at is this Cartesian copy. So this is when you have this process, it just copies things, it takes in one, punts out another, copies of them. And the important axiom with this is that if you have a generator on the left, you can again push it through and have two copies. But if you look at the diagrams for this, well, you could not tell that they were the same just by looking at them. The connections are all messed up. Like this F, oh, now there's two Fs. Like what? And although we have this axiom, we can't just absorb it into our graphical notation. So for that, we need to define our diagrams a little bit more rigorously so that we can use graph rewrites rather than just considering diagrams up to isomorphism. And this has been done, well, over the past probably 10 years, this has become quite an interesting thing. So first of all, back in sort of 2012, Alex Kissinger was working on string graphs. And then more recently, he and some other people like Pavel Sobotinsky have been working on sort of hypergraph representation for diagrams with various structures. And so you might think, oh, well, it's all been done. Everything you're doing is useless. But again, this is not quite the case, because these diagrams are based in this compact closed structure, which I mentioned earlier, with these sort of bendy wires that we can go. And one problem that we already know is that this means we can make bad diagrams. We can make outputs go into outputs. And then another problem with this is that if we consider our Cartesian axiom we had earlier, this copying morphism, then with the bendy wire, we just sort of push it around, and now we have something which takes in two things and sort of merges them into one. And in our model, that's not sound. We don't want that. So what we're going to do is take these hypergraphs and make them a little bit better for our use. So before I move on, have you got any more questions about all of that?
Yeah, so is the trace just a loop from the output back to the input?
Yeah, it's just, let's set the picture up again. So you just take say the first however many wires you want to do, and take them around and join them back up to the input.
So I didn't quite get that, because you said in some cases this is going to blow the circuit up.
Oh, that's only when using this sort of other way of bending wires, this compact closed.
Oh, I see.
This is different. Okay. Yeah, this is a compact closed thing where we have these bends, but that can mean we have bad things. So instead, we're using this trace. We did everything all in one go, rather than, say, constructing it from two of these curved ones.
Yeah. Okay. Thanks.
Okay. Great. Right. So hypergraphs. What is a hypergraph? Well, hypergraphs are very fashionable these days. So a hypergraph, just like a normal graph, we have vertices, but rather than having edges as just these one-dimensional lines, edges are now these big boxes, and edges can now connect to any number of vertices you want. So on the left of an edge, we have the sources, ordered sources. So I have one. This one here, this one is the first source. This vertex is the second source. And on the right, we have targets. So this edge here, that's the first target. This is the second target. And then this is just sort of a generalization of normal graphs. And you can already see how we might want to use this to represent our string diagrams that we had earlier. Now, one last thing we need to add is these labels, or labeled hypergraphs B, apparently. We have this signature again, like before, and we just put the labels to our edges, provided that the number of sources and the number of targets is the same as the inputs and the outputs of our original morphism. But we can also do morphisms between hypergraphs, and this will be very important when we do our graph rewriting later, as this is all based on morphisms between hypergraphs. And you can see this sort of smaller one, meaning embed it inside this bigger one here. You see this vertex here, this vertex maps here, this one goes here. And we just need to ensure that all the sources and targets of the original graph are preserved. As you see, well, they are, because we've still got this one here and this two on the other side. Then if these maps are bijective, then we know the hypergraphs are isomorphic, which is very important. But unfortunately, just these regular vanilla hypergraphs, they're not enough for our purpose. For example, say we can just split wires like this, because there's no requirement that vertices can only connect to one edge, one left and one right. We can do things like this. And in string diagrams, unless we've got some extra structure, we can't just arbitrarily fork wires. We need to have a specific morphism or generator that will split them for us. So this is not allowed if we were to use this for our trace context. And another problem is that, say we have these interfaces where we know that anything not connected to an edge on one side is sort of an input or an output. So we have inputs of the whole thing here and outputs here. But there's no ordering to these vertices. The only ordering we have in hypergraphs is on the sources and targets of an edge. These guys are just sort of dangling and doing nothing. So that's something that we need to add. And to solve both these problems, we're going to introduce the notion of an interfaced linear hypergraph. And so they look very similar to our original hypergraphs, except now we've got two sort of additions. So most notably, you can see we have these two edges. There's alpha for inputs and omega for outputs. And these sort of collect, these act as they were if normal edges. They have an order, and we can order our interfaces however we want. And the possibly more subtle changes are now all of these vertices need to have a left connection and a right connection, and that's it. They can't just dangle. We can't just have things forking arbitrarily in two, because that means we wouldn't be able to use them for our string diagrams. So we have to make sure that everything is left and right only. And again, we can use our signature to label everything up. Morphisms are again very similar to before, and what is important to note here is that we don't need to preserve the interfaces, the order in the interfaces, because we want to be able to stick things onto it on the left and right. So while we have to preserve the sources and targets on all the white edges, the grey edges they're not as important, and we can just sort of change the order as we want. What's more, if we have bijective maps and the interface is now preserved, then we have an isomorphism. So the important thing that we want to show is that this hypergraph language is sound and complete for symmetric traced monoidal categories. Because otherwise, when we used it, we might suddenly find ourselves getting these degenerate hypergraphs that represent weird terms that we don't want. So what does this mean? So soundness, first of all, is possibly the more simple one of these. So if we have two terms that are equal in our category, then when we interpret them as hypergraphs, they must be isomorphic. So what does this mean we have to show? Well, all it means is that we have to show that all of the axioms of symmetric trace monoidal categories that I showed you earlier, they all hold in our hypergraph language as well. So we need to define some operations on our hypergraphs to sort of correspond to those in the category. So first of all, we have composition. If we have things with the same outputs on one side and the same inputs on the other, we can join them together and then make ourselves this composed hypergraph here. Our identity is just this single vertex, which is only in the input and the output. You see how that just, again, has no effect on the graphs if we just compose it on the left or the right. It's just going to be the same thing. We can stack our graphs on top of each other, and all that needs to do is just put them on top of each other and combine our interfaces, and we're done. And the empty identity unit, monoidal unit, whatever you want to call it, this is just this empty hypergraph with nothing in it, because again, that will do nothing to our graph. Symmetry is just this graph where we swap over the orders of the interfaces, and we could build bigger ones just by composing them all together with different identities and things. So then the final thing is the trace. Now everything has been fairly simple up to now. It's been pretty, oh yeah, you just bash them together, you put them on top of each other. It's easy, right? So I think, oh, trace, again, you just sort of maybe take the output and the inputs and connect them together in some way. And that is what I thought for a good 7 months. And then I got some reviews back for a paper, and they were like, no. I was like, oh, that's a bit sad. And what's the problem here? Well, the problem is concerned with the trace of the identity. If we have an identity, then we trace it, we get this sort of loop, we get this closed loop. And you might think that this is just like, this is pointless, this isn't connected to anything, we can get rid of it. And that might be true in some cases, and indeed it was back in the 80s apparently. But then they realized that no, this isn't the case. We actually do need to keep these loops around just in case. And this poses a problem, because we can't do stuff like that with vertices and edges, because in our hypergraphs we need vertices to connect to edges. We can't have a vertex going to a vertex because that's not a valid hypergraph. And the reason that this arises is because, almost as we're a victim of our own success here, we've absorbed identity morphisms into these wires, these no edges, which is great for the most part, but in this case we need them back. So for this reason, we're going to introduce this concept called homeomorphism, which was used back in Kissinger's string graphs, and we're making it have a comeback now. If we have just an identity here, we can expand it and add in this special identity edge, which just represents the identity. Things go in, the same thing comes out. And we always be able to remove this edge as well, unless they're connected, which I'll show in a minute. So now this means that we can do our trace. We can take our graph, we trace it by adding in this identity edge, and then if possible, we can squash it down and just make this one here. And this allows us to do trace by identity, because it means we have this followed by the trace. I mean, I have this loop here, which is still a hypergraph. And we're not allowed to squash this one down, because otherwise we then have an ill-formed hypergraph, which would be bad. So that's the trace. So what we want to do before we can show soundness is we want to be able to interpret terms in our category, these f.g tensor b or whatever, want to turn them into hypergraphs. And we do that with this interpretation functor from the category of terms to the category of hypergraphs. And so we have this term we have from earlier. Very, very obviously, you might think, yeah, it clearly corresponds to this hypergraph. And then what you need to do is just check through all the axioms. It took me a very long time. It was like all of April. It was not very fun, but it took a very long time. But eventually, yes, all the axioms do hold, and it seems pretty obvious when you look at it, really. So that's good. We have soundness. Everyone okay with all of that? Todd's looking a bit confused.
No, I was just reading it.
Oh, that's fine. Good you're paying attention. So okay, so we have soundness, that's good. We have one side of our language done. So next, of course, we've got to do completeness the other way. That if we have hypergraphs, they always correspond to terms in our category. So the first step to this is called definability. And it means if we have an interface linear hypergraph, then we can always retrieve a set of corresponding terms in the category. And the reason that it's a set is because, as you remember, there are lots of different ways of writing down our diagrams in this one-dimensional string, but they all correspond to the same diagram. So any graph we have is going to correspond to potentially many terms. So how do we do this? Well, all we need really is just an algorithm that we can derive some sort of term from any graph. So first of all, we're going to set an order on our edges and sort of stack them on top of each other. So for this one, let's say we have this one is the first edge, this is the second. And then we can define this tensor here, or this fork one, tensor by the join one. With this order we have. And next, all we do is think, well, the outputs of these edges have to connect somewhere else in the graph, right? So we need to trace them all around, like this. Take a big trace. And then obviously what goes in this gap? Well, we just need to hook up everything with the right input. And that means we need to define this sort of shuffle construct which shuffles everything around and ensures that everything is the right way around. If you want, you can follow this around and make sure I've drawn my diagram right. It's a long time spent in ticks making that. Not sure it was worth my time, but I hope it was. Let's just give it a go. Let's just try this one. Goes into the top of that. Yeah, so if one's right, they're probably all right. So let's move on. So the definability proposition is that if we have this functor which turns hypergraphs into terms, then if we go back into hypergraphs again afterwards, we get the same hypergraph. And hopefully you think, yeah, should be right. But that's not all of completeness. So remember we have this set of terms that we got from our graph, and this arises because we can set any number of orders on the edges. We could swap them over. If we have lots of edges, we're going to have lots of orders. Importantly, we need the morphism we get out of this procedure. We need it to be unique up to the equational theory of the category. They all need to be equal. But fortunately, all you need to do for this is just show that if you swap two edges over in your stack, just this F and G here, us being swapped over to G and F, then you get the same thing. And you do, because all that's in this box here is just these wires, and you sort of shuffle them around a bit. And the order of the edges doesn't really affect the connectivity in any way. It just means you have to move things around a bit more. So whichever edge order we pick, we're going to get the same morphism out of it, up to the equational theory of the category. So what does this give us? This means that if we go from have a hypergraph, go to a term and back to a hypergraph again, it's the same hypergraph. And if we start with a term and then go to a hypergraph and transform back into a term, we're going to get a term that's equal to the original one. So good. Now we have a sound and complete graphical language for symmetric traced monoidal categories. Yeah. So has anyone got anything to ask about that? So we can move on to the real fun bit. So remember at the start, the whole reason we're doing this is because we wanted to do graph rewriting. We wanted to be able to represent these extra axioms sort of properly, rather than just going, oh yeah, you can cut that bit out and smash it in, which obviously mathematicians really hate. I love it. Mathematicians hate it. And apparently I have to be a mathematician now, so I've got to do it properly. So our extra structure, as we remembered earlier from our Cartesian copy naturality axiom, we represent it as this rewrite rule equation. We have this thing on the left is f followed by the copy. We can then replace it with this on the right, this copy followed by 2 of that morphism generator. And we can do that, well, first of all, we have to translate them into hypergraphs, and as we've seen before, that's very easy. And then we need to rewrite everything. So before I do it with all our interface linear hypergraphs, I'll first just show you how the procedure works with normal hypergraphs, because with the interface ones, there's a little subtlety which needs to be tackled first. So first of all, a rewrite rule is just, we have our left-hand side on the left, our right-hand side on the right, and in the middle, we sort of have their common interface, as it were, this vertex for the input, the output, and this is also the same on the left and right. And this happens because if you have a rewrite rule, both sides of it have to have the same inputs and outputs, because otherwise, when you replaced it in the graph, then suddenly you'd have these dangling wires, and then your graph would fall apart. So this is how you would represent a rewrite rule formally as this span. And then if we have sort of a set of axioms, we can just convert them all using our interpretation functor. So say we have this left-hand side of our rule. Now we want to identify a matching of this. We want to see where this occurs in some big graph. And how do we do this? Well, we just do this with a morphism between hypergraphs. We say, oh, this F goes into there, that one goes into there, and all the numbers are the same, right? So this 1 is there, that 2 goes there, that 3 goes there. So this is a valid morphism. So we know that this subpattern does exist in this graph. And so we should be able to perform rewriting. So how do we do that exactly? So first of all, we need to assemble everything. Well, we need one more first. We need to have just this other morphism to denote the interfaces. Because remember that these hypergraphs don't have interfaces. So we sort of temporarily create them for this procedure. Just more dots getting up here. So to do rewriting, we assemble all these components into this big, well, half completed as it is, commuting diagram. So on the top, we have our rewrite rule. Remember before, we had this left-hand side, and we have this right-hand side, and their shared interface. And then remember, we had this matching morphism from the subgraph into the big graph. and then we have this sort of formality, this interface here. So the first thing that you want to do when rewriting is to remove the instance of the left-hand side inside this big graph. You want to sort of cut out this bit and just leave a gap, because that's where we're going to be pasting in the right-hand side later on. And the way you do this is that you compute what's known as the push-out complement, which means that of this thing, this is this sort of route we can take. This is sort of the opposite. This graph here plus this graph here make this big graph. And we've essentially cut out the left-hand side of the rule from this graph to get this. As you can see, so the 2 here used to connect to the copy, but that's now gone because there's now a hole, and then the 1 which used to connect to the F is just sort of currently just sitting there on its own because he's not connected to anything. And then all we want to do now then is just, as I said, paste in the right-hand side of the rule. So here we have these morphisms here to here and here to here. So all we do is compute the push out, which is just combining these graphs together to make this big graph. So you have the 1 here, it went to the copy on this one, and it went to nothing on this one. So in the final graph, it goes to just the copy. I think we've got a more interesting one. Yeah, the 2 goes to, on the left, it has the F, and on the right, it has the fork, the join even. So we have 2 on the left, it goes to the F, on the 2 goes to the join. So this is the combination of both of them. And that is our finished graph, our rewritten hypergraph. And then we just do G or squiggly H if we can rewrite like this. Now, not all structures make it so easy to do this. Like, we need to have some properties that the category satisfies in order to do rewriting. And this is quite nicely packaged up in the framework of adhesive categories. And the most important thing that these adhesive categories have is that, let's scroll back a bit, this push-out complement, this chap here, this is unique, which means that if we have a matching of this small hypergraph inside the big one, we always have a unique graph at the end of it because of this unique push-out complement. Because if you had 2, then suddenly you'd start diverging, and doesn't bear thinking about. So we want to make sure that all our categories are adhesive. And fortunately, the category of these normal hypergraphs, it is adhesive because of some trickery involving a slice of a functor category and all these properties which no one really cares about. But unfortunately, our category is not quite adhesive. And the reason that this is because our interfaces, as we said before, we don't need to preserve their orders or anything, which means that when we do try and do a push-out complement, everything's going to get swapped over perhaps, and then we can have multiple different orders and multiple different resultant hypergraphs, which is not what we want. But rather than moping over this for a couple of weeks like I did at the start of December, we could just do the rewriting in our category of hypergraphs instead. So if we have an interface in a hypergraph like this, we sort of just trim off its interfaces, just take them off, as you might imagine. And then obviously we want to get them back at the end. So we have this way of sort of keeping track of our interfaces. And then if we have an interface like this, you might think this looks very familiar to what we had in our diagram before, then we can always just plonk our interfaces back on with the order that we had. Now, that might be a bit confusing. Has anyone got any questions about that? Because I might have gone through that a bit quickly. Yeah.
Is there implied to be a kind of ordering on the kind of dots that are just?
Yes, the idea here is that we're sort of keeping track of sort of in the background. So because we know this one was the first input, then this one here is the first input, and this is the second output. This is the first output, sorry, and this is the second output. And we're sort of keeping that in mind because we have this sort of function here.
Okay. Can I ask a question?
Mm-hmm. Yeah.
So I am slightly confused about the ordering of. So you sometimes say that the order is something that we need to preserve, and sometimes you say that it's something that we can reorder things. Is there a quick way to say when order is useful and when you don't care about it?
Mm-hmm.
Like, is it just a tuple of outputs, or is it like just a set of outputs?
Well, normally when we're sort of combining these hypergraphs and things and composing them and stuff, we don't really care about the orders because we want to be able to switch them up. Because say if we were composing a hypergraph with a symmetry, then we want the orders to swap around. But when we're graph rewriting, this is probably the one time that we don't want that to happen because we want to preserve everything just to get this one unique hypergraph out of it. That because when we're rewriting, sort of you don't swap things around, you just take out a hole and put something back in it.
Right. Okay. I see. So then, but most operators will have like different values in the outputs, right? So how do you know which one you want to connect to? Like, basically, my question is about the choose axiom, right? Like, if you have a set of outputs, then you have to be able to tell which one you are connecting to, right?
Yeah. Well, they're ordered sets. So when we have, if we're combining two together, we're composing two together, then the first output goes to the first input of the next one, and the second to the second, and so on.
Okay. I think I understand now. Thanks.
That's good. Right. So we know how we can sort of translate to and from our interface hypergraphs to these regular run-of-the-mill hypergraphs. So in this case, a rewrite rule, we have like this, like we said before, we have this on the left, and then we rewrite it to copy the F across on the right. Now we just translate that into the span of regular hypergraphs that we had before. So now it gets all into one nice big diagram. So we start off with this, so we have our matching morphism of the instance of our rule inside our big graph. And we also know at some point we're going to need this right-hand side of it. So first of all, let's translate it into the regular hypergraph interpretation of the rule, as we said in the last slide. And then the next thing to do is then we translate our interface hypergraph into this regular one using this trimming functor. We chop off the interfaces. And then we need to keep in mind the order we've got on our interfaces, because otherwise when we got to the end and we're trying to convert back, then we wouldn't know what to do. So we have this arrow here, this IO, which means that we just sort of know that this 1 is the lowest and this 5 is the highest. And then we have a diagram in the middle, very much like we had before. We can just do our rewriting. We can compute our push-out complements, cut out the left-hand side of the rule, and then paste back in the right-hand side of the rule. And then the last thing to do, obviously, is to retrieve an interface hypergraph out of this. And hopefully you should be able to see that now we have this ordering here, the 5, we follow the 5 through. The 5 also then goes to this one. So we know that this 5 is the first input, and then the 1, say, follow it through, 1 into this one here. We know that that's the second output, so we know the orders that we have on our interfaces, so we can recover them. And then all we do then is just stick the interfaces back on with these orders that we've recovered. And then we have our rewritten interface linear hypergraph. So yeah, so that is just rewriting with our symmetric trace model categories. So then, got any questions about this sort of big diagram that I've just thrown on the screen? No. Good. So obviously I'll be doing this all with these props, these categories with numbers as the objects. So we have wires coming in and the number of wires coming out. But can we generalize that to arbitrary symmetric trace model categories? And well, yes we can. All we do is just put some labels on the vertices and make sure that these vertices all match up when you're doing composition and things, and then you have exactly the same procedure as before, but now you have for any objects rather than just numbers of wires. So we have defined a sound and complete graphical language for symmetric trace monoidal categories. And this means that we can reason in these categories purely graphically, which is much easier than trying to navigate these long strings of text that you can't decipher. And we can also add extra axioms to our categories, which is often required to add structure, using these graph rewrites, as we said before. And yeah, we just formulate the axioms as we write rules, perform a rewrite, and then you're done. You've done it. So that is all. Thank you all for listening. I've got two clap emojis. That's all I need.
Thank you. Any questions?
They understand too well.
Yeah, I can ask some more questions.
Go for it.
So I think I missed at some point the motivation for going from graphs to hypergraphs. I mean, sort of superficially, it looks like you just add dots to all the edges, but I'm sure there's some better reason for it than that.
I think as in like sort of versus like the graphs that we had back here. If I go back to the slide. So many slides. It's like these sort of ones versus this one.
Yeah.
Or
Okay.
I think it's just a matter of maybe ease, because I think with these string graphs, with the ordering of sort of edges on vertices, I think there was some sort of tight maps going on and complexity behind the scenes. Within the hypergraphs, obviously the edges implicitly have these ordered sources and targets, which is what we want to model our morphisms in our category. I think it's just a matter of ease and of defining all the operations and things.
I suppose another thing as well is they're not just dots on one particular edge, because you can see on the right-hand side you've got one like on a fork. So
Yeah.
It's not just that they're on like an edge; it's that they can be in the middle of several edges.
Yeah, so it might be sort of clouded a bit by the way we do them, because then we sort of reduce this back to only one on the other side. But
That's the linearity, I guess.
yeah,
Right.
so yeah, in full-blown hypergraphs, we're not using this subset as this. Yeah.
Yeah. Oh, I guess with graphs, do you lose like if you have a non-commutative operation like implies, do you end up losing that or something?
Like what? Sorry.
If you have a Boolean implies operator, so it's non-commutative, is that where you need?
Well, I think they had something to do with that, because they would, yeah. Kissen just said, oh yeah, these are we can do stuff with them for another categories. So there is some ordering involved, but I just think it's a bit more complex than just these of, oh, we have a set of ordered sources, we have a set of ordered targets, we're done. Rather than having to say, oh, here's our type map.
Yeah, I also got two questions. So first question is that, is there any terms that cannot be translated to this hypergraph representation?
Well, in the whole point is that all terms in the symmetric trace model category can be represented as hypergraph, as our interfaced linear hypergraphs. So that's the soundness.
Yeah, and the second question is that, so if you translate the terms into this hypergraph representation and you do some rewrite and translate it back, you will always get equivalent terms, right? But will that be like totally the same term, or it's just equivalent but maybe different?
Will be the term, if you go back into them, then the term you'll get will be equal up to these axioms that you've got. So if you have f equals g in the category, and then you go f into a graph, rewrite, and then back to g, then that term will be equal up to all the axioms in the category to g.
Okay.
Do your rewrites, I mean, this may have just been answered, but it reminded me, do all of the rewrites relate to rewrites in the kind of term semantics as well? Like, can you end up with a graph that doesn't relate to a term by rewriting a certain area? So I'm thinking of things like beta reduction, for example, where you end up with a kind of middle step, but you kind of ignore when you do it in the term form, but graphically you don't ignore.
They should always rewrite into stuff that has an equivalent term, because I hope so, because that's one of the big results of the work. Yeah, because we know that the rewriting is always well defined to this unique term, and unique graph even, and we know that each graph has a corresponding term because of completeness, so everything should all work out fine.
Okay, so any rewrite done anywhere at any stage, basically you can convert it back to a term, and that's an equivalent term. Okay, that's quite cool.
Okay.
I guess
Any
now
more questions?
now I'm not completely hogging the questions. I can ask another one. So when you had this problem with the self loop, you said you fixed it by having an edge for identity. It looks like you could also instead choose to have an edge for trace, which at least to me seems more natural, given that it's kind of a more complicated operation. But did you?
When you say edge for trace, what do you mean?
Yeah, well, I don't know exactly, but
in effect, this sort of, I mean, for the main use case, I guess effectively it is an edge for trace.
Are there some complications involved, like because trace kind of goes backwards?
Well, the idea is that we want to basically this vertex needs to go. We want something that comes out of this here. This needs to go into wherever this one connected here. So I'm not sure as what really a trace edge would be in this.
It probably wouldn't look that much different, but it'd be so somehow you'd only be able to use it in one of these backwards tracey sections rather than just anywhere.
But actually, we do actually use these elsewhere as well. I didn't mention it because it was a bit in all the things.
You use the identity diamonds elsewhere.
Yeah, they're important for in graph rewriting. Which I didn't mention this is that the matching it has to be a monomorphism. You need to be able to have all the maps need to be injective. So sometimes you do need to have these.
So the problem is with the identity, not with the trace, really. And so the diamond is a way of fixing that problem because it's with the identity. Because I guess what James was saying is if there's a problem with trace, like trace is the thing that should have the fix, not the identity. You shouldn't sort of patch up where the problem's being sort of appears, but where it's actually being caused.
Yeah, actually it's weird because first of all, this diamonds were introduced for this graph writing stuff, and then when I realized that, oh wait, there's a slight problem here, like, hold on, rather than having these random hacky things, why don't we make them part of the whole framework and make them less hacky? And that's why they're there now.
Thanks.
Yeah, that was a good question and good answer. I think you've answered everyone now.
You're all welcome.
Yeah, I think if there are no more questions, then thanks George for this brilliant talk, and thanks for everyone for joining this meeting. And if you have any further interest on this topic, you can contact George offline. Thank you, everyone. Bye-bye.